Again, I'd like to welcome Alastair Stanley, talking about meta-generators, playing safe with long sequences. Thank you very much.
Hi, everyone. My name is Alastair. You can also call me Ali. And this is my first conference, first time speaking. So thanks for the welcome. It's been a really great experience so far. This is my plan for the talk. A brief intro / refresher on generators, why we use them. An example that is something similar to an issue we actually faced for various corporate reasons, not exactly the same. Why it hurt us and how we then fixed that issue, and then came up with a much better long-term, more elegant fix. I'll try to make sure we get to the end of this talk, otherwise I've mistitled it horribly. And since many of you might be wondering what I mean by meta-generators, quick preview is that I'll be talking about concepts and some code patterns that you can hopefully take away with you. This is not some magical library that I'm going to provide. There are reasons for that I might go into if I have time. If you're interested in taking this on and actually standardizing it, let me know. Or if you've worked on the same sort of thing, we can talk about it afterwards. Come find me. So generators, quick run through. What are they? There is a strict definition. Generator is an iterable, sure. A subtype of iterator, which is a little more refined, the definition. And generally, we create them with generator functions, with the yield keyword instead of return. I'm sure many of you use generators or have used them. If you haven't, I'll show some code later on, which is an example of what generators are. Got a strict definition, but I'm kind of going to ignore that for now. Essentially, I'm going to be talking about things you can iterate over that create things on demand. This is really lazy loading iterables. And this is what a lot of people mean when they say generator. A lot of things that we think of as generators actually aren't strictly generators, but I'm going to be talking about them as well. If you wanted to create a generator-like object manually, this is the sort of thing you'd do. We need that iter and next dunder. And essentially for generators or generator-like objects, this lazy loading property means that all the fun stuff happens down at the bottom there. That's where the computation happens when we ask for the next element in the iterable. Not there. For a lot of other types of iterable, it'll happen there. That's where everything really happens. All the values might be pre-computed. We don't do that in generators. So we use them because they save on memory. We can produce the values one at a time. We don't need to store them all simultaneously. This is something I think we're all familiar with. We also sometimes get a time save when using generators. If we find what we're looking for early or meet some other termination case, we don't need to compute any other values that we're not going to use. So we can save on time as well. But possibly the coolest thing about generators is they can be infinite. Hopefully, the code example there is large enough. If you can't see it at the back, we have a generator function called alwaysBlue, which, when iterated over, simply yields the string blue for all time. And also, I'm going to mention the itertools library, which is great for this sort of thing. It has a function that does exactly the same thing, and that's going to be a repeating theme in this talk. The example I'm going to talk about is inspired, like I said, from a real-world issue that I experienced. And it's about comparing documents. I mentioned that I work in news engineering, so you might be able to guess which documents we were working with. But I'm going to be talking about pieces of music as my parallel example. We start with asking, how can we modify a piece of music? And hopefully this will work. Cool, speed up, slow down. Change the pitch of a piece of music, or the key. Make it major. More adventurous. And finally, we can invert the shape, which literally means turning it upside down. If you'll allow me some artistic license for the last bit, a guy called Rachmaninoff actually did all that, took another piece of music and wrote a variation on it with those modifications. They're generally considered different pieces of music. He changed enough, but what does it mean to not change enough? Let's say we wanted to test for copyright infringement, or whether someone has copied our music illegally. Well, maybe let's just choose a subset of these transformations. I'm going to take these ones at random. If someone's just changed the pitch of our music and chopped out a couple of notes, maybe we say that's not enough and it's the same piece of music. And we can check whether they've done this just by trying some combinations of these two transformations and seeing if we get a match. How would we do this? Well, changing pitch is the easy one. We can just write ourselves a generator that spits out each pitch change in however format we want it. 1 octave up or down would give us something like this. Again, if that's not clear at the back, a simple change pitch generator function that iterates over semitone change values in the range 1 octave either side. And we're using generators, lazy loading iterables like range. Again, not strictly a generator, but does the same job. And so our memory use is very low. And no matter how large our range of semitones is, we're not using any extra memory. The other bit's more interesting. If we're removing some notes from our piece, we might just start with 1 note, or even 0, the null transformation. But let's say we start removing each note in turn from the piece of music, one after the other. Then we try every pair of notes, then every combination of 3 notes, and we can keep going up to some limit. Obviously, if we remove all the notes from a piece of music, we have changed it significantly. And let's say maybe the limit is 10% of the notes. I am aware that code snippet is, they're getting increasingly smaller. To remove k notes from a piece of music in every combination, again, there's an itertools function that does exactly what we want, combinations. And we take all the notes, tell it we want every set of size k, and it spits them out one at a time. It's a generator. So we should expect some memory save there. We do this for each value of k, from 1 up to some limit. And I've written it out in full there, but there is again, an itertools function to do that. So what is this memory save? It's actually not quite as good. For combinations, we are obviously returning tuples of notes of size k, so we've got to use some memory to build those. Bit concerning that it's on, which is the number of notes in the tune, and not ok. But there we go. And that second one, we chain them all together. No extra memory use, so that's great. Generators doing their job. Put it all together. We want any combination of these transformations, pitch changes, and note removals. We want a product, so we can use Itertools product function. And they're just taking each generator, the pitch changes and the note removals, and producting them together. And then the memory kind of explodes. So memory usage goes through the roof here if you're not careful. And why does that happen? Where have we gone wrong? A lot of you might know already what the problem is, and that is products, for example, are expensive. We're not getting that memory save that we expected. This note removals, it can actually get quite big. Combinations, n choose k, can get quite a big number. So for a 100-note tune, that's around 20 trillion elements long. But it's a generator. We're not storing all of them at once unless we pass it to product, which does exactly that. It tries to store them all in memory in order to iterate through it multiple times. So that note removals, if we're careful with it, it shouldn't do us any harm. We should be able to just get the elements one by one. But if we're not careful, if we try and look at it all at the same time, it's going to freeze up our machine or kill the process. I like to think of it a bit like a particular famous sneaky-haired character. That's my quick impression. If anyone has a suggestion for the name for this kind of Python Medusa, please let me know. I haven't come up with one yet. So why does product do this? It kind of has to. If we write out something like this for x in iterable 1, then for y in iterable 2, to try and go through every pair, doesn't work for generators, because you can only go through a generator once, and this tries to go through it multiple times. So instead, we need to store all the values for that second iterable in order to go through it multiple times. And this must be done. You may try to build up the storage as you go to try and spit out some values, yield the first couple at least, before things get out of hand, but it's really just kicking the ball down the road. You haven't really solved the problem there. And here's a quick list of some of common functions that we use with iterables that, on the right-hand side, preserve the benefits of generators in that they only look at the values one by one. On the left-hand side are the ones that are dangerous. They will use up all the memory that you have left if you're not careful with how you use them. There's an asterisk on reversed on the bottom left. I'll explain why in a few minutes. So what did we do when we encountered this problem? We have two generators that may be very large, but we want to get the product of them. One way around, of course, is to just completely refactor your code and move the logic around. But what if you don't want to do that or can't do that? One thing that may come to mind is we just clone the generator, right? Has anyone here tried to Google this at any point? How do I copy or clone a generator? I did when we first saw the bug, and all the links were purple. So I think that means that some people must have looked it up before me. So this code snippet, just import copy at the top of our naive product. And instead of iterating through the second iterable in the inner loop, I make a copy of it and iterate through that copy. We get a type error trying to pickle a generator object, and this is very sensible. Conceptually, if you try to clone a generator, you could create a lot of problems. Maybe that generator is reading from a file or some other generator, some single-use consumable. If we make a copy that's also reading from that same place, they're going to collide. You're going to mess up the first generator as well, maybe. Use up all the things that it's trying to read. There are other problems with this. It's just not a good idea in general. So we can't just clone it. You could pass in the generator function instead. So we just rebuild from scratch an identical generator at each stage, each time we want to loop through it. And case by case, this might work depending on what your generator function does. It may suffer the same problems as the last example, where we're trying to read from something that can only be iterated over once, and we get colliding readers. But this is a bit cleaner. It's the solution we actually used at first. It's the one that we decided on to solve our problem. But you might be able to see that if I were to use this as a generic product function, and I wanted to use it with lists or dictionaries, I've got to wrap them all in a function. That's not very nice to have to do, so it's a bit messy. And a second problem is you may just not have access to that generator function. It's possible. So we can do slightly better than this, and that's where the more elegant solution comes in, which I'm calling meta-generators. What do I mean by this? Kind of iterable, again, but I'm kind of throwing away some of the other stricter definitions of generators and adding that we have extra contextually useful functionalities on our lazy loading iterables. This is the same generator pattern I showed at the start, and we're going to change it up slightly. For a generator to be a bit more useful, to be aware of how it may be used, we might say, well, maybe I want to go through it more than once. If I'm writing a lazy loading iterable that I know needs to be generated multiple times, or iterated through multiple times, I could get it to just reset itself every time we call the iter dunder. So this can be quite useful. This naive implementation of product now works for this lazy loading iterable. We can add copy dunder. And while a generator can't do this, if in our use case we can sensibly copy our generator, even if we're reading from a file and we think that maybe we can copy that file or do something else here that makes it work with multiple loops, we can do that too. And this other naive product implementation now works as well. We haven't had to change that code at all. We just change our lazy loading iterable that we're passing in by making it a little more aware of how it might be used. So product, we can now write our own product implementation that does not consume all of our memory, preserves that benefit of generators, and we can kick it over to the right-hand side. Some of these other ones are a little more complicated, but cycle, which simply iterates through a generator or other iterable, then starts again and again and again. At first, with a generator, needs to store all the values in order to go through a second time. We can rewrite that with either of these styles of meta generator and kick it over to the right as well. So that's kind of what I'm doing for the rest of the talk, is trying to get all the ones on the left over to the right. Reversible, lazy loading iterables. There was an asterisk on reversed on the other slide, and that's because this already exists in the very common range function. These days, range is a lazy loading iterable. It's a bit more clever than a basic generator in that it has this implemented very smartly. It doesn't need to just read out all the values one by one and then flip them around. It can actually do that because it knows its start and end value and step. It doesn't need to do all the heavy lifting. If we can do that as well, if our use case allows, we can write a reversed dunder and save ourselves a lot of pain. And yeah, range also has the contains dunder, which means that if you're checking for a value in a range object, instead of just spitting out all the values one by one until we find what we're looking for or don't, it knows how to do that smartly, saving on the memory use. So reversed sometimes stores the values, but if you pass in something that's self-aware enough, knows how it might be used in that way, it's kind of already on the right-hand side. So really, we want to try and write our functions for iterables in that same sort of way if we can. Again, a lot of these may not work in the general case. There are exceptions to a lot of these rules. For the vast majority of cases, though, a lot of these approaches can help us a great deal. So reversed, the function, will check if an iterable has that reversed dunder. Use that, and if not, it just does the dumb thing of reading out all the values and flipping them around. So write your functions that way, and it'll be a lot better for you. I've been talking a lot about infinite or very large generators here, or lazy loading iterables, and how you can avoid killing your machine by doing these, using these approaches. But generators of any size can still see a benefit by using this. So don't just think, oh, my generators are not going to be trillions of elements long, so I don't need to do this. You can write more efficient code with any size of it. And I think that's it from me. So yeah, as I said, if you've been working with this sort of thing or would like to pursue some form of extra standardization, please come and speak to me about it. Also, feel free to find me. I will be over at the Bloomberg stand for the next hour and a half or so, over lunch perhaps. And I look forward to seeing some of you there.